Hello and welcome. My name is Dr. Micah Stevens, and I am the Disease Testing Coordinator at Sierra Gold Nurseries. In the past few years, we have worked hard to develop and optimize the state-of-the-art tools we need to sample and test our budwood orchards in-house for little cherry disease. Now, some of you might be curious about how here at the nursery we are performing these tests, so I thought I would take you through how we are using cutting-edge technology to ensure our trees are disease-free. The foundation of our testing relies on the principles of PCR. For those of you that might not be as familiar, PCR is a method that takes the DNA of any organism and exponentially amplifies target regions within its DNA. For a PCR reaction to be successful, you need 4 basic requirements: your template DNA, an enzyme to copy the DNA, guide molecules or primers, and the building blocks of your DNA, your free nucleotides A's, T's, C's, and G's. This reaction takes place over successive stages or cycles where the DNA is split apart, your target region is duplicated, put back together, and the whole process is repeated in the next cycle. Most PCR reactions have anywhere from 35 to 40 cycles, by which point, if your target DNA is present, you will have made millions and millions of copies. RealTime PCR is a variant of PCR that allows us to measure this amplification in real time, and we will see why that is important in a minute. One additional component to our RealTime PCR test that sets us apart is the incorporation of a probe that is essentially a key that recognizes a certain sequence of viral DNA. Probes are short DNA sequences with a fluorescent dye on one end and a suppressor on the other that target and bind to specified regions of template DNA, in this case, viral DNA. The fluorescent dye acts as a signal, while the suppressor prevents the fluorescent dye from being detected prematurely. Once the probe binds to the target DNA, the fluorescent dye is released and it is detected by the PCR machine. As the PCR cycle number increases and the amount of amplified DNA grows, the fluorescence signal becomes stronger. Probes and primers can be multiplexed to ensure adequate coverage of diverse viral variants. Here at the nursery, we can screen for over 16 different plant pathogens using this technique. The use of this probe allows real-time PCR to become a very sensitive and powerful technique that can detect the presence of virus even in small quantities. If the viral DNA is not present, the probe has nothing to bind to, and so no signal is detected. Despite the fact that real-time PCR fluorescent dyes and probes are sequence-specific, a considerable amount of background fluorescence occurs during most real-time PCR experiments. It is critical to bypass or account for this background signal in order to glean meaningful information about your target. This issue is addressed by 2 values in real-time PCR, the threshold line and the CQ value. The threshold line is the level of detection or the point at which a reaction reaches a fluorescent intensity above the background levels. This is literally a line in your graph that represents a level above background fluorescence that also intersects your reaction curve somewhere at the beginning of its exponential phase. And the CQ value is the PCR cycle number at which your sample's reaction curve intersects the threshold line. This value tells how many cycles it took to detect a real signal from your sample. Real-time PCR runs have a reaction curve for each sample, and so many CQ values are generated. Each sample's CQ value is then calculated and charted. And another really important to think about with CQ values is they should not be compared across different PCR runs or labs. CQ values are inverse to the amount of target nucleic acid that is in your sample and correlate to the number of target copies in your sample. Lower CQ values, typically below 25 cycles, indicate high amounts of the target sequence. Higher CQ values, above 30 to 33 cycles, mean lower amounts of your target nucleic acid. High CQ values can also indicate problems with the target or your PCR setup. Both the threshold line and the CQ values are integral for analyzing real-time PCR results. Finally, I wanted to show a real-world example of what our typical real-time PCR results look like for virus detection. Here we see the results of 2 samples. First, a positive control that has little cherry virus, and a second unknown sample. The plot on the left has the relative quantity of virus sequence present, and the right plot illustrates the amplification curve of our two samples. As your PCR reaction proceeds and the signal being read from our probes increases, you expect to see a nice smooth curve until it begins to flatten off when the components of your reaction begin to become exhausted. So in this example, you can see the positive control has a low CQ value and a high relative quantity of the virus, while the sample has an undetectable CQ value and zero relative quantity of virus signal. From this, we can conclude the sample is most likely negative, as both the CQ value and the relative quantity indicate no viral DNA is present. Well, that's all the time I have, but I hope I have shown you how seriously we are taking the threat posed by little cherry disease by rigorously and routinely testing our budwood orchards using real-time PCR combined with virus-specific probes in order to provide pathogen-free trees to our growers. Thanks for your time, and please come find me at the Sierra Gold booth if you have any questions.